Organizers, good day. I trust you found the networking break useful and you got to visit the exhibition center. We're continuing with the rest of our program. We're at day 3 of the National Space Conference. The theme is entitled Space and the Future. Earlier on, we heard the special lecture delivered virtually by Ms. Ponso Marupeng on the space and sustainability. And just before the break, we spoke about sharing current space education and outreach activities, methods, and techniques. We're now onto the technical session, which is all about the advancement of space to harness future technologies. Before I introduce the moderator, I believe one of the panelists is still outstanding. Is Ms. Tongwane Namane in the house? Oh, sorry, you were not here. Thank you so much. It is now complete. Please join me in welcoming onto the virtual stage the moderator for this discussion. He is Dr. Naeem Aji, PhD Environmental Science, Senior Researcher from SAPI, Southern Africa. Over to you.
Thank you so much for that introduction. So I think it's afternoon already. So good afternoon, ladies and gentlemen, and a warm welcome to Technical Session 3, the advancement of space to harness future technologies. We have an exciting lineup of topics this morning, ranging from biostatic radar solutions to SAR constellations, remote sensing applications in ecology, to improving LoRa IoT devices. And these also highlight the developments and advancements as we step into the 4th industrial revolution. So just a quick, 2 quick announcements to the audience. Please don't forget to post your questions by going to slido.com and using the access code on screen. And to the presenters, I know we're running behind schedule, so kindly stay on time. So getting started with the first presentation. Our first presentation is MicroStar, a biostatic radar solution to commoditize SAR, which was presented by Mr. Villinel. Willie joined the CSIR almost 24 years ago and is currently the Chief Radar Engineer. He also serves as a member of the IEEE Radar Systems Panel. So join me in welcoming Mr. Villinel.
Good afternoon, everybody. Hope you are comfortable on this 1st of September spring day, and hope you all remember to wear something colorful. In my case, it was stars. So, because we are, after all, at a space conference. Okay, so I'm going to be talking about MicroStar, and I have this title at the bottom, Space for Inclusive Growth, and I think if we go to the next, it should come up and say, SAR for inclusive growth. Okay, and that's actually what I want to be talking about. And it's a bit awkward because the speaker next to me is going to be talking about Fleet SAR, which is a satellite SAR constellation done in the traditional way. And I'm sort of starting first, and I have to talk about, and I'm talking about what's coming after all of these satellite SAR constellations. I really want to talk about, the next big step that's going to happen in SAR. Okay. But before I do that, you heard my name is Villinel. I'm at the CSIR. I've been there since 1999. I am the Chief Radar Engineer there. I have a couple of my team here as well. From the SAR team, we've been working in SAR specifically for South Africa since 2015 to get us to the point to have a synthetic aperture radar capability with which we can go to space. And on that slide, you saw on the very far right some designs, and so that is of our satellite SAR that we are currently working on, called SAR-C, a project that's sort of done with lots of industry and supported by DSI. Okay, so I'm not really going to talk about all the rest of these three. There's a lot of things that we've done. If you come to our stand, we can have a decent chat if you are interested in synthetic aperture radar. Maybe let me see that. By show of hands, who have seen a SAR picture before these ones? Okay, there's quite a lot of people in the room. By show of hands, who has used a SAR picture ever? There's one over there, a couple of there. So the interesting thing is, that's the thing about SAR. It's been around since the 1950s, and yet seemingly it's only recently started to make it all the way to becoming mainstream. And the reason for that is SAR used to be a thing that only really the big governments could consider, and it used to be a thing that cost lots and lots of money. We talk about satellites of 2 or 3 tons, and you spoke about probably $30,000, $40,000 per image. I mean, I'm pretty sure if I ask the question, who out of his own pocket has paid for a SAR picture before? I think the answer is going to be nobody in the room. Okay. I mean, I worked in SAR for a long time, and I've never paid for one myself, out of my own pocket. Okay. So the question is, how are we going to get that right? How are we going to get SAR from being this amazing tool that allows us, like this picture shows, to see at night, and to see through clouds, to see through smoke? Okay, that's what SAR can do. This picture, it doesn't matter if it was raining, I could still take that picture. It doesn't matter what, it could be very bad weather, and you could still make that picture. Doesn't matter if your enemy, if you're in the military guys, it doesn't matter if your enemy is, blowing out smoke or hiding even below his canvas tent. The SAR sees straight through the canvas tent. Okay, incredible technology that we can use. Nowadays, doesn't matter if you're hiding beneath the foliage, and this is interesting, even at X-band, people previously believed that foliage penetration required a very low frequency radar. This picture, recently released by ICEYE, is an X-band picture showing how with a long dwell, if we look at the scene for a long time, and we basically show different angles as we go past the scene as different colors, on the right-hand side, all the man-made things in the forest stands out. Okay, incredible things that you can do with SAR. And the other thing is, most of you in the audience have not seen SAR doing video before. SAR is no longer a thing that is just making a stationary picture. With airborne SARs nowadays, we produce videos of the world, and in those videos there's a whole contents of rich information that gets added. And so this is where SAR is going, even in space. So recently, this by the way is pretty much a similar approach to the long dwell approach, and recently ICEYE also released some videos that they make using SAR from space. So that's where SAR is going, just generally in the monostatic configuration. So the question is, why am I then talking here about something different? When, if people can do all these wonderful things, why am I even saying, let's do something even more incredible? And the answer to me is still in that answer of, well, it's like 40,000 rands for an image. And I think if you really want to make this something that everybody uses and that the small-scale farmer can afford to use, then we need to find a way to make it cheaper. And to make it cheaper, we need to get rid of the fact that you have this huge satellite that has 100 dB path loss down to the ground, 700 kilometers away, energy goes back and forth, and you have to compensate for that, which means now you have a huge antenna, typically in space. That antenna is like 5 or 10 square meters, and you end up having a significant transmit power, like 4 kilowatts. So now you build a satellite, and that satellite ends up being heavy. And yes, the modern guys have managed to bring that down. People like ICEYE and Capella have come up with all sorts of innovative ways of bringing that down. But they're still collecting the data up there in space, and then they have to get the data down, and then there's huge delays from the time that they get the data until you actually get your hands on the data. And there's lots of cost involved and lots of middlemen involved. Okay. So the way I see it, and the way I believe the future is going to go, we basically say, no, let's not do that. We put a transmitter in space, and it's only a transmitter. It's a dumb thing. It's not going to do much. You're just going to really command it to the type of waveform that you want it to transmit, particularly the type of resolution you want to achieve and so forth. And then we reduce the path loss that you have in this equation by putting your receivers close to where you need them. So effectively you end up with drones like that, or even cell phone towers, small little masts next to a field, now being able to create a SAR picture. Now, people will immediately, that knows a bit about SAR, will say, okay, how are you going to get that right? Because, you need movement, a stationary thing. How is it going to? But the point is, the movement comes from the satellite in low Earth orbit that's creating the Doppler. So it gives you enough Doppler that you can still make the picture, okay? And that allows you to now consider a complete different mode of doing SAR. And it works. And there's just 2 examples. One from the CSIR, where we just had a very crude experiment. We took our airborne system as an illuminator, sorry for it going on took our airborne system as an illuminator. I took Wi-Fi antennas and something like, I don't know, 2,000 rands worth of receiver technology, 4,000 rands SDR type things. And we made this first picture ourselves in sort of 2 days, just to show that it'll work. There's an example from a guy in Sandia, National Laboratories, there's the quote. The traditional SAR system there is the picture from the spaceborne SAR. That spaceborne SAR illuminated the scene. He used that little receiver that you see in front of him on the mountain and created that picture. And the interesting thing is that picture contains a lot of information that one doesn't. Okay. Because of the angle at which you're imaging, the shadows are, you get much more pronounced shadowing, which means you can sort of tell things height a lot easier in the picture. Okay, so it works. Biostatic SAR is something real and that now has been shown and, that you can do it. The advantages are many. Handheld devices can make SAR. We can have a high mast on like every cell phone tower. Imagine every cell phone tower in the world creating SAR pictures around it every day, and what that would be able to do for us. Even something like a high ship mast, now you can have a ship that's silent. It basically doesn't need a nav radar anymore while it's out there on the ocean, meaning that its chances of getting ship-jacked or hijacked, basically, is pirated by somebody, is a lot less, because nobody can actually pick it up through their ESM receivers. This is what pirates do. Okay, the other thing is, if you're the military guys again, this military started the conference, if you're the military guy, well, you can have a passive receiver that nobody knows that you're listening. So you can make these pictures and nobody knows that you're listening and nobody knows that you're doing it. Okay. But there's a whole set of other advantages. The one thing is zero latency. So effectively, you're making the image right there where you need it. You don't have to send it anywhere. You don't have to have other people involved in the process. You just process it right there on your iPad and you have the picture. Okay, immediately. Every one of those things will be a video SAR, because effectively, to the receiver on the ground, that beam coming past and illuminating you acts like a long dwell all of the time. Okay. Interferometry becomes single pass instantaneously, because we can have two antennas and we can, from those two antennas, immediately derive height, which means we don't have to have, and by the way, we can also remove the effects of the atmosphere that comes, because we are measuring that atmosphere with our antennas on the ground. So we can directly correlate through that. Turns out that you can not have atmospheric effects in this interferometry things, which is a big thing in SAR. And we get continent level coverage on every pass. Because these satellites now, current SAR satellites, they are transmitting like 5 to 7 minutes per orbit. So you've got a 96-minute orbit, they're only transmitting 5 to 7 minutes of those orbits, okay? But in this case, because we can make the satellite a lot smaller, we basically can get the satellite to be on whenever it's over land, for example. Meaning, we can image the whole of Africa, or we can illuminate the whole of Africa almost every time that satellite comes past, and every receiver on the ground can make a picture. So we can have a lot higher coverage rate than we can have a traditional SAR. Okay, so what are we doing about this? Well, we started a program together with SES a long time ago, actually already, and we're trying to look for funding, and it turns out that this idea is still, I think, a bit too novel or a bit too far to the front end for people. So when you speak to people, to funders about this, they're like, yeah, we're not so sure we can fund this yet. The market's not ready for it. But yes, we've started coming up with solutions and designs for how you would build a satellite that can do this. There's a picture of that satellite using one of the subarrays that we were intending to build a traditional SAR satellite with. So effectively, instead of having 15 antenna panels, we just need one for MicroStar. Okay, and it will come up with modes like I'm showing at the top there. So you can still get 1 meter resolution pictures out of this satellite, the receivers on the ground. And you can still do wide swath things if you want. If you had receivers that's high enough, you would be able to image quite a significant area of the maritime coast, for example. I'm not going to go into detail. I'll talk about one example of an application we looked at. So for close-to-shore maritime surveillance, one of the big problems with current SAR satellites, they can't detect the small vessels. In this case, if we put a receiver on every cell phone tower along our coast, we would be able to create a very cheap way of doing maritime surveillance over the first 20 kilometers, specifically looking at the small ships. Okay, and what I'm showing there, and we've done the sums for this, and we showed that you'd be capable of doing that. I'm also just showing one small military example of what a biostatic SAR image of a tank would look like there at the top, done in simulation. Okay. I'm going to, in the interest of time, not talk through the other technical details of things here. We can, if you have questions about how this works, you can come and have a chat to me. There are, of course, drawbacks. There's always, anything that you do in life is a trade-off. And there are some trade-offs here. One of the trade-offs is there's only particular areas around your receiver where you get orthogonal range and Doppler. In other words, where you'll get a nice looking image. Okay. There are some areas, as the satellite comes past on the sides here, where effectively those range and Doppler things align completely and you have no resolution, no ability to resolve. Similar to traditional SAW that can't really see in front of the antenna. You have to look to the side in a traditional SAW. Okay. But as I said, if you could do this and you build these cheap receivers and you put them on every red dot that you see on the map here, that's where there are cell phone towers. You don't even need to have them on every red dot. You can just imagine that we can quite quickly have a network of sensors very cheaply if Vodacom and MTN wants to play along, because effectively we can place these things. They're on the internet backbone. There's already, you can already get the data centralized. You don't have to add any power infrastructure or anything else like you normally would do for other radar. And you're just adding a passive receiver, so you don't need transmit licenses for that side. What we require is just a transmit license for the space segment. If you want to do agriculture, here's an example of what we could do in an agricultural area. I'm showing on the right-hand side there a test site that I identified above Grabo. People that's in the space community know this area pretty well. Lots of high economic value activity happening there. One mast up there will give you coverage that looks like that. The ability to basically look at SAR data over almost all of the Grabo area. Okay, using just one well-placed mast. Okay, so I started off by saying we're going to make it cheap, but now I'm saying everybody must buy a receiver. The point is, you only buy the receiver once, and then thereafter you install the software, and then every image you get, you just may be paying a small license fee. Okay. And the receivers won't cost an arm and a leg. They maybe will just cost you, I don't know, I mean, right now I can go out and buy this thing from RT, SDR processor card, what's that, 100,000 Rand? Okay? And that's where technology is now off the shelf. I'm pretty sure if we do this as South Africa in production, we can do this a lot more cheaply. So I started off my talk by saying, I want to see SAR for inclusive growth in South Africa, okay, for space in Africa. And my dream is this, that we as a country become the force behind biostatic SAR in the world. That we create the industry that sell these receivers to everybody. That we create the satellite constellation that we can control and with which we can drive a complete new economic sector. And that is what I believe MicroStar can do. There are a lot of naysayers that will tell me, no, but wait, there are all these other transmitters already. Can't you just use Starlink, or can't you just use somebody else's like GPS or some other transmission? And yes, you can do passive biostatic SAR that way, and you will not get very good images, okay? For various technical reasons, but it has to do with the waveforms that were never designed and the power levels that were never designed to give you a proper SAR image. So it really would be beneficial to have a network of SAR radar transmitters that are created from the start to give you high quality SAR imagery. And so that is where I'll end off. I think what we need to do now next as a country is to start developing biostatic SAR applications, to find the ways to get to these cheap receivers. Sorry about that. To develop a launch to a Pathfinder mission, maybe just 3 satellites launched in constellation. They'll be a lot cheaper than the current things we have on budget for SAR satellites. And then to demonstrate with this some niche applications so that we can scale globally. Thank you very much.
Thank you to Vili for highlighting the value that biostatic SAR can bring to commercial SAR. Our next presenter is Ms. Tongwane Namane. She is a director at the SES Aerospace Group. As you probably know and visited their booth, SES is a private South African company that provides turnkey commercial Earth observation and communication satellites. since 2008. Ms. Tongwane will be presenting the business case for Global Visioning Systems, FleetStar satellite constellation. Ladies and gentlemen, please give a round of applause for Ms. Tongwane Namani. Thank you.
Great, good afternoon, everyone. I suppose when we speak about gender equity, I'm quite privileged to be able to speak on Spring Day and looking quite colorful. So greetings to all the ladies. Well, thank you, Mr. Nell, for setting the scene. He's gone and taken all the technical details, so that means I'll be able to speak about the business aspect and the commercialization aspect. I'm a director at the SCS Aerospace Group, and I'd like to say my title is that I deal with commercial finance for outer space activities, which sounds pretty cool when you're trying to determine the business case. So what that means, in essence, is that I need to bridge the gap between what you have as your academic institutions and your institutions, your research institutions like the CSIR, and start to speak to users, businesses, as well as financiers who are then able to invest in these systems. So we're looking at calling FleetStar Earth observation redefined as global visioning systems. So when we walk into an environment where we have a commercial client, we have to now start explaining, which is not scientific and jargon linked, what Earth observation is and what remote sensing is. So the basic part is that the same way that you have a global positioning system, so a GPS, we call Earth observation a global visioning system, or a GVS. FleetStar is a synthetic aperture radar satellite constellation, which is digital infrastructure projected to develop next-generation space systems. Currently, it is a project which is a private-public partnership between private sector as well as a governmental agency. The project value is currently sitting at about $840 million US. CapEx, which is initial investment, is at about 345 million. That translates to about 4 billion rands, and we're looking for an internal rate of return of around 15.93%. FleetStar is focused on being a greenfields project that intends to design, manufacture, launch, and operate a fleet of 12 small satellites in low Earth orbit around the Earth. Currently, South Africa, as a country, and various countries across the continent actually rely on international service providers for data and data coverage. And what this means is that you can't get on-demand data. The spot data and data sets that are available are based on a group client basis and not necessarily on an on-demand basis. So we look at the elements around data sovereignty. So FleetStar will not only add to the country's ability to monitor its oceans, agriculture, industry, and human settlements, but will also give South Africa and countries in the continent that would work with the FleetStar constellation the ability to have data sovereignty. Okay, the project is currently in development phase. We have 3 co-development partners at the moment, so MPSA, SCS Space, and the Industrial Development Corporation of South Africa. And we're currently inviting parties to join as co-developers and or funding partners. The difference between the two is that co-developers actually develop in terms of the technology, and then the funding partners will come in from the financial aspect and revenue generation capabilities. So the model also ensures sustainability by making sure that we do generate high skills and expertise, and make sure that it's retained within the project. And this is the part that this whole entire conference we haven't been talking about numbers. So there is a traditional pathway that has been within the space sector moving from being military-based and academic and scientific-based to what you call the commercial space economy or new space, and where we would have the capability to have a look at the commercial applications. So currently, the market is being projected, and this is the entire space industry, at about 200 billion. This is by McKinsey, and would probably increase to about $1 trillion odd US dollars by 2030. Divided into ground equipment, the launch industry, which obviously is one of the most famous if we're going to look at companies like SpaceX. But then we have satellite manufacturing capability, which is available in South Africa, quite a critical sector. And then the majority of the factors has to do with satellite services. The market values for defense, as you can see, are quite substantial, 4.7 billion for defense. Scientific is still in there at 1.3 billion. And the commercial aspect, I've put it there as undefined because we have quite a large market opportunity. Right. One thing that is a benefit around SCS and working with some of our partners is that we're end-to-end. That means that we're able to be prime contractors in terms of the design manufacturing, as well as operations. We're currently, developing launch capability within the country, and we work with partners with that. We're able to have operations and then, of course, services. So the majority of partners do either fall within services. However, the satellite manufacturing capability as well as operations capability is something that we're excited about retaining within our space. Right, so system infrastructure from an investment perspective deals with space operations, of course, but this is more on the private sector side, specifically around ground control, applications processing, and having mission control. I think at this juncture, I would like to speak about the capabilities, of course, of artificial intelligence coming into the system, and how we could utilize, recurrent neural networks, machine learning, to be able to process satellite data for use. I'm just going to very briefly have a look at this slide. We're not talking about nanosatellites at the moment. In fact, the satellite sizes are between 350 kgs to around 600, which is quite large satellites. What this means for us is that FleetSAR will firstly be potentially one of the largest satellite constellations globally, which I think is something to be very proud of. ICEYE is currently projected to be launching 8 satellites, and we're sitting at 12. Right, so coming through to the use cases, I mean, there are data requirements that fall over quite a wide spectrum of applications. As I mentioned when I started looking at, what's currently happening in the market is that there's quite a few applications in the academic and scientific sphere, and only and government sphere, however, not necessarily the expanding on the opportunities available in the commercial markets. Right, so that would be energy, engineering infrastructure, maritime, of course, and location-based services, which are growing exponentially. I'm just very quickly going to go into how the various applications actually contribute to making a socio-economic impact, not specifically just with the FleetSAR constellation, but looking at sustainable space programs. So these are the Sustainable Development Goals, and we project that we would be able, in this particular project, to be able to make an impact in several numbers of the Sustainable Development Goals, specifically around quality education that's developing high levels of skills and expertise. I think, as we've seen with our partners at the CSIR, that is quite technical and niche. Looking at developing industry around innovation and infrastructure, as well as looking at decent work and employment. What I've added onto this, which is speaking about socioeconomic impact, specifically in South Africa with the National Development Program, is the Agenda 2063 of the African Union in terms of the Africa that we want, and we've linked and aligned with Aspiration 6 and Aspiration 7, which is making sure that whatever we do in terms of space and space sustainability is people-driven and relies on the potential of African people. I think we have fantastic skills and expertise in the market. We're just looking further here at what some of the, from a commercial perspective, what some of the user requirements could be. So, you know, with precision agriculture, what is being utilized in terms of optical, in terms of radar, as we, has been stated, that SAR data is quite, well, the development part has been quite expensive, but what's really exciting has to do with the ground spatial resolution. We've started to see even further resolution actually going down to 0.5 meters in terms of what you are then able to see. All right, more government focused is obviously your maritime and domain monitoring. Had quite a bit of talk about ship detection and tracking. That's in the maritime domain. And then specifically monitoring activities all the way to border monitoring. This slide here, well, these two slides do go into quite a bit of detail in terms of the user requirements from commercial business and use cases. And the reason why it's so important to have a look at the business case and commercial applications has to do with the ability to fund sustainable programs outside of just purely the government space, outside of just purely private industry that works with government clients, and making sure that this gets to filter into the commercial area. Right. So one of the large aspects, of course, utilities, well, energy, mining, infrastructure, and engineering, and the type of information that we have been able to collect is what it's particularly used for in terms of the applications, how it could impact whatever the use cases are, and things like revisit times and the types of data sources and data analysis that is required. All right, there was someone here, well, earlier on from the Space Generation Advisory Council who said there's not quite young people in here, but I think just in terms of the youth and being excited, about the capabilities that we are developing in South Africa, and for benefits of the continent, we're extraordinarily proud and really, really find, firstly, the constellation itself, the development of the constellation itself, quite exciting, but also just in terms of the use cases being quite exciting as well. Right, so I'll just very, very quickly just talk about SES Space and the fact that we're developing quite a few constellations, including, well, we've had a talk about SES AgriSense as well as MicroStar, and where we have quite a few development partners who are working with us to make sure that we're able to maintain this capability within the country. And with that, I'd like to thank you very much for spending this time listening to me, and if anyone really wants to speak to me about financing opportunities, either wanting to come on as co-development partners, or wanting to look at the commercial applications, or wanting to look at leveraging and taking advantage of the funding opportunities, I'd really encourage you to come through and speak to me. That would be great. All right, thank you, ladies and gentlemen.
Thank you, Ms. Tongwane. It is encouraging that Fleet Star wants to be the largest constellation globally, which will only encourage development and real-world applications at scale. So moving on, our next presenter is Professor Tina Stander, Professor Stander is an associate professor at the University of Pretoria. Over his career, he has published over 90 publications in various local and international journals. He will be presenting on the oscillation-based built-in self-testing, a promising approach for RF systems in orbit. Give a round of applause for Professor Stander.
Thank you very much. Any Monty Python fans in the audience? Yes. And now for something completely different. Forget about that, that's not important. For the benefit of many people in the audience, I'm going to take you very briefly through what is built-in self-testing and what the challenges are that we face. So before we consider radio frequency electronics, before we consider satellites, I want to talk about a car. I have a car in my garage, and I have a question about this car. And this question I have about this car is whether it can meet some sort of defined performance requirement, in this case a minimum speed. So what do I do to test whether the car can meet its requirement? I take it to a road, I place it in a test environment, I apply some test stimulus, in this case I step on the accelerator, and I watch the speedometer. If the speedometer reading matches or exceeds my criteria, then I know my test is successful and the system meets its capability. What if I wanted to know the same thing, but I can't put it on a road, I can't step on the accelerator, I can't put test stimulus into the system, and I'm blindfolded, I can't see the speedometer either. Welcome to the challenge of built-in self-testing, where we measure how fast a car goes by checking the tire pressure and reading the dipstick. What can built-in self-testing tell us about our system? Again, we're not talking about RF electronics yet, we're not talking about satellites. What do we want to know? Because we design our tests around what we want to know. We distinguish broadly between fault-driven testing and specification-driven testing or performance-driven testing. For fault-driven testing, we want to know, is there a fault somewhere in the system? I'm driving my car home from the mall, it's making a sound. Where is it coming from? I have no idea what's wrong, but I know it's not supposed to be there. So, is there a fault somewhere in my system? Where is the fault? I could take it to a garage, a trained mechanic can listen to it and say, oh yeah, spark plug, or carburetors, or yeah, engine gearbox, or whatever. So they can find where the fault is. How bad is the fault? Can we diagnose how bad the fault is? Is it reparable? If it can be repaired, what kind of inputs do we need to apply to repair the fault? Irrespective of that, I can limit myself to performance testing. How well does it work? Can I still drive this car at the required 30 or 60 or 120 kilometers an hour? But I can also do a relative measurement to a performance requirement. It doesn't really matter how far this car should be able to get me on a specific amount of petrol. Can I make it home? Yes or no? So does it work well enough to check whether we meet the specification? And all of these apply to the testing methodologies that I will discuss in a few minutes. Why do we focus on radio frequency electronics? Well, without radio frequency electronics, there's no point to a space industry. You can't communicate with satellites, you can't control it, you can't get data from them, you can't uplink data, and many of your payloads as well rely on radio frequency electronics. So if you're going to invest time and effort in having good, reliable systems you can test, that's as good a place as any to focus your attention. What are the risks to any electronics, but specifically RF electronics in space. There's always shock and vibration during launch, and that can ruin a system if you don't plan for it carefully. Extreme thermal cycling that these electronics go through in orbit, vacuum outgassing if you don't choose your materials carefully. They can outgas, they can affect your performance over time. The one we've looked at most over the past couple of years is ionizing radiation, not specifically the single event upsets or single event effects that the digital engineers are worried about. We're worried about long-term buildup of damage due to total ionizing dose damage or displacement damage. And there's a good reason for that, because this is from Swartvoort's database on CubeSat launches, or NASA satellite launches. Many of launches are actually a partial mission loss or a mission loss, but so they make it into orbit. So the initial shock and vibration are survivable. But why do they fail? And can we learn something from the system in orbit so the next one does not fail? And that's why I believe built-in self-testing is an important consideration even for CubeSat applications where we use commercial off-the-shelf electronics. So what happens to these electronics? We have studied the degradation of these devices at both a device level, a transistor level, and at the circuit level, which is typically the amplifier and phase shifter we've studied. So the transistors, they degrade quite predictably. They give you lower gain. They exhibit more parasitics than what you're used to as the damage increases. We used beta radiation, not because it's particularly representative, just because we had the source available to us in the lab. If we translate that device level damage to a circuit level, we find two important things. The one is, and this is a 60 gigahertz low noise amplifier in silicon germanium bi-CMOS. If you do want to send something to Jupiter, you go for SiGe. This and gallium nitride are virtually indestructible. We had to radiate that up to 15 megarad to get substantial damage. Conventional CMOS is less resilient. But it degrades over time eventually. And what we found was, yes, the gain of the amplifier reduces, but the bandwidth reduces as well. So whatever we do to test these systems has to consider both effects. How are these systems measured in orbit or just in service currently with built-in self-testing? There are three classical approaches. The one is source testing, where you have a source that accompanies your system wherever it's transported to, wherever it's applied, and it injects a source, an RF tone, into your system, and you measure the output, and you see, does this conform to what I expect from a nominal system? And it works. It's some overheads. It's especially difficult to get a highly reliable RF generator to fly with your electronics, and whatever damage your device is subject to, your test generator is subject to as well. So it's a bit of a chicken and egg situation if you try to evaluate the damage. The other approach, very common, is the loopback test, where you use your transmitter as a test source for your receiver, and that works provided that you have a transmitter and a receiver as part of your system, and B, that these two operate in the same band, which is not always the case. There's also a surrogate or a dummy approach, where you do an indirect measurement of some electronics which is co-located with your main system. The assumption there is that the damage builds up on both devices simultaneously, and it works. It's low overheads. It doesn't interfere with your normal operation, but then you have to ask yourself, is this really a good approximation for what my system is supposed to do in service? Am I measuring the right thing? Or might I be measuring a dummy variable when I should be measuring the true variable? What we focus on is on oscillation-based testing. Those of you familiar with Barkhausen's criteria will know that any device in feedback with sufficient gain and the right phase will oscillate. Many amplifier designers in the room would have learned the same thing by accident more than anything else. And this is exactly what we do. We take our device under test that's connected in a system, we switch it out of its nominal state with an astable feedback network with a very well-known reference, and we make sure that whatever variability in our system we have is limited to our device under test, that our reference is very stable in comparison. And then by looking at the system dynamics, we see that both the power and the frequency of this oscillator and many other oscillator parameters are a function of my nominal device. And if I know how my device should respond, any deviation of that can tell me that my underlying device here, my main amplifier in this feedback scenario, has a fault in it. We can look at the frequency, we can look at power and the harmonics of the RF oscillator, and we can look at time series data. The advantages of RF OBT are then that we don't need an RF source to test. We can test the true RF performance of our device, so we don't do surrogate testing. We can do testing on inaccessible nodes, and we can do testing for systems that are inaccessible for testing otherwise. So we can do in-situ testing. There is a caveat to that. We can't digitize an RF oscillator output, but we can digitize harmonics if we filter them out. So we rely very heavily on good RF filters, which we can do, and good RF power detectors, which is something else we can do. But variability is a problem. If you have a nominal oscillating tone and you know any deviation from that means there's a fault, it's fine. The problem is sometimes you have a situation where my nominal distribution of oscillation or power or any other metric that I measure overlaps with a fault condition. So now you have to distinguish between these two when your measurement could be either or. Let's say I take a measurement in the middle here. Am I measuring that condition or am I measuring that condition? And that's a key problem that we've been addressing the past few years. So one of our earliest works, we looked at implementing oscillation-based testing in a 2.4 gigahertz CMOS amplifier in 0.35 CMOS. Not a very new fancy process, but a process that's what we know very well, we can characterize very well. We found a couple of things. The test methodology is quite sensitive to process and temperature and supply rail variation, the so-called PVT variations. So whatever way you devise to interpret your data has to compensate for that variability. And if we look at a full temperature range, we looked at -40 to plus 85 degrees Celsius, we found that over our full test range, by only looking at threshold discrimination, above a certain threshold we reject, below a certain threshold we accept, or vice versa, we can get test escapes of 1 in 20 and yield loss of 1 in 52. Test escape is where we do not reject a faulty chip. Yield loss is where we reject a non-faulty chip. So it's a start, but we certainly need to do better. We need to look at other data. We redid the experiment, this time using a RF PCB, also 2.4 gigahertz LNA. There you can see there's our main amplifier schematic, there's our feedback network, we measured it here, and we looked at the harmonics in our oscillator. We asked ourselves a different question. Now we're not hunting for faults. Now we want to estimate performance, and can the technique and the measurements that we can take with this technique give us performance estimates? Turns out it works incredibly well. That is the correlation between our measured forward gain and one of our differential measurements. That's the correlation between 1 dB compression, which is a measure of the linearity of the device, as well as one of our measurements. So it seems like this technique is better suited to performance estimation than to fault detection. But we found something else which is interesting. If we don't bias it as a harmonic oscillator, we can get a self-quenching oscillator with a periodically varying envelope. And that will become important in the next slide. Not the next slide, the slide after that. We also applied it to a system level. We used our BIST low noise amplifier to act as test source for the rest of our receiver. And we can pick up all sorts of faults in the system with this way. High impedance nodes between elements in the receiver, loss of local oscillator power, degradation of the low noise amplifier gain, all sorts of things. So it can be extended to a system approach as well, even if your full system does not work. We also use it to calibrate phase shifters. So if you can measure something, you can control your measurement, then you can calibrate, and there's another application we looked at. We also looked at classifying oscillator responses by finding faults, and we found that deep learning on a time series works very well. We get very good estimations of which component in our circuit is faulty by looking at deep learning data. But what was interesting is that the startup condition of our oscillator is important in estimating that data. So remember, at RF, we cannot digitize these individual time series, but we can digitize an envelope. So that will form the basis of our next stage of our research. Can we determine more about our oscillators by looking at the time series envelope variation? Just a few summary notes, and that's it. Thank you very much.
Thank you, Professor Stander. So moving along quickly, just want to remind the presenters to please stick to time. We are short today. Our next presenter is Dr. Philemon Tsele. Dr. Tsele is a senior lecturer at the University of Pretoria. He has over 20 research articles in various local and international journals. And Dr. Tsele will be presenting on the integration of active learning and machine learning for hybrid retrieval of biophysical variables in protected mountainous regions. Please give a warm welcome to Dr. Tsele.
Good everyone. In this presentation I'll be sharing with you some of the experimental work we've been trying to do on the developing some biodiversity monitoring tools, particularly in the rangelands of South Africa, using satellite data. So the title date is, long as it is, integrating active learning and machine learning regression methods for hybrid retrieval of grass biophysical variables using Sentinel-2 data. So biodiversity monitoring is a key component of protected area management and planning. So the biophysical variables, such as the leaf area index, leaf chlorophyll content, and so on, are regarded as essential biodiversity variables that can be measured by use of remote sensing. And they also provide, or they serve as essential input into climatic models for determining ecosystem productivity. So these biophysical variables are not only important for understanding vegetation health conditions, structure, growth, and so on, but they are also important to facilitate effective monitoring and management of natural vegetation at different spatial scales. So the natural heterogeneous canopies, like the grasslands of South Africa, are characterized by native multi-species grasses. And such environments are characterized also by, they are analogous to actually rangelands, which are ideal for livestock production and grazing for animals. And as a result, in such environments, it is critical to assess the areas where there is a change in response to climatic effects, also to quantify the amount of above ground biomass, and also to monitor the functional status and diversity of the rangeland vegetation communities. And some of the monitoring and mapping is already being done by use of remote sensing technology. And here are some of the models that actually, at the global scale, they generate this vegetation biophysical variables, such as the leaf area index, the chlorophyll, fractional vegetation cover, which are very important in the management of vegetation protected areas. However, the challenge is at our scale, or particularly in our rangelands, we have found that these global algorithms, they have they give retrievals with large uncertainties. So that is one of our validation studies which we found, which prompted the need to develop locally parameterized types of models that are transferable between the sites. So if we are able to develop such type of models, it's a step closer towards developing biodiversity monitoring tools in our rangelands. Yes. So the current hybrid schemes for retrieval of land products, such as the leaf area index, chlorophyll, yield inadequate retrieval accuracies, particularly in heterogeneous environments, and that is what we found and reported. So for example, these hybrid retrieval schemes, such as the Sentinel-2 Level 2 prototype processor, we found that it gave inadequate retrievals of vegetation, leaf area index, chlorophyll, and vegetation and fractional vegetation cover over heterogeneous grasslands in South Africa. So generally, these hybrid schemes, they rely on retrieval methods that are trained using large amounts of simulated data. So the challenge now with these retrieval methods, which is part of the reason why they do not work in some environments, particularly in our environment, is that this large amount of simulated data contains not only informative samples, but it also contains noisy and redundant samples. And therefore, there are several techniques which are available, which could be explored in trying to select only the informative samples or the best possible samples from a large pool of simulations, which we can then use with these retrieval methods. So the aim of this study was to compare the non-parametric regression algorithms and their integration with active learning, which I'll explain later, for the improved estimation of leaf area index and chlorophyll content over a multi-species grass canopy in Maragell National Park. So this is the study area where we conducted our experiments. So, so our study, as you can see, the area covered the surface area of 67,000 hectares. It's quite a mountainous area with slope variations of 0.3 to 14 degrees. The area has got a total of 136 total grass species. And on the map, you can see these are the sites that we visited to collect our field measurements. So we collected 68 field measurements, and each sample contained information about the leaf area index, fractional vegetation cover, chlorophyll content, as well as species identification at the plots. And the study was done during peak wet. The field data was collected during the peak wet season of 2001. So this is the overview of the methodology that was followed in the study to try and improve on the estimation of these vegetation biophysical variables in the heterogeneous grasslands. So it is a hybrid retrieval workflow which incorporates active learning methods, and the methodology is twofold. At first, we ran the simulations, which simulated the spectral response based on our input parameters of leaf area index and the chlorophyll across the entire park. Then we used those simulations with the retrieval algorithms in order to do the mapping So from the retrieval, we did the validation to see which of the retrieval algorithm was the best in terms of the retrieval accuracy, and therefore we chose the best and did the estimation of LAI and chlorophyll across the park. Then later, we took the best machine learning algorithm and then incorporated it with active learning algorithm. So with the active learning, what we did is from this pool of thousands of samples, we applied the active learning methods to pick only the informative ones and then feed into the best regression algorithm to get reliable or improved estimates of LAI and chlorophyll. So what's shown here is the parameterization of the model to get those simulated reflectances, as mentioned earlier. So we use the ProSail model. As said there, that ProSail is one of the radiative transfer models that use radiation laws to accurately describe the spectral variation of the canopy reflectance. And it does so by considering quite a number of parameters which are listed on the first column. So those parameters, they are leaf-based and also canopy-based. So during the parameterization process, we used our own field data, particularly for the leaf area index and chlorophyll, in order to also improve on the quality of the simulations. And then we also used some of the information from the metadata, from the Sentinel-2 data, that is the solar zenith angle, the view zenith angles, and the rest of the parameters we used, the parameterization was based on literature. So we relied quite on the parameters published in this study by Masemola, and that is because their study site shared similar characteristics with our study site. For example, their dominant grass species that were found or reported in their paper were also found in our site as well. So we considered their information quite useful for our model parameterization. So what are active learning techniques? So active learning techniques, they use the selection criterion algorithms to select what they call intelligent or smart samples or informative samples from a large pool of training data. So the general process of how active learning techniques work is shown in these boxes here. You can see that at first it starts with a large simulated training database. So we use 30,000 simulations of reflectance. And then the active learning algorithm, they start with a small subset of labeled training samples, right? So in our case, for example, we started with 100. Then from there, the learning techniques will apply different selection criteria, which are shown here. So each one of these algorithms, the criteria is different. So they apply the selection criteria, which pulls labeled samples from the large training data set, which would then be matched with a training data set, which is considered to be optimized. So this is a list of the what you call selection, the active learning methods, which are divided into diversity criteria algorithms and uncertainty criteria algorithms. So the diversity criteria algorithms, what they do is, in a nutshell, they consider diverse samples. So from the initial subset that is there, when they go to the pool of simulations to pick the samples, they go for unique samples. They ensure that no duplicates are selected. And then the uncertainty criteria algorithms, what they do, they first start with samples that have got a large uncertainty or samples with the least confidence, and those are discarded. And then it only leaves with the informative samples. So in this study, we evaluated 6 non-parametric regression algorithms, and these algorithms have been widely used in the literature for estimating vegetation biophysical variables. And as you can see here, they are categorized into linear and nonlinear. And what these algorithms, they have in common as non-parametric regression methods is that they are data-driven methods. They define the regression function based on the input data, for example, the spectral data vis-a-vis the biophysical variable of interest, and they optimize the regression model through a learning process using training data. So these are some of the results, the simulations, how they look. So what you see there is the spectral variation of the canopy reflectance across the park as a function of the leaf area index and the chlorophyll that was collected in the field. And these served as a very important input into the retrieval algorithms. So, so this is the results of the retrieval algorithms that were used and for retrieving LAI and chlorophyll. So what you can see there, the ones which are made in bold, these are the most accurate, the algorithms that gave the most retrievals. And for LAI, it was the partial least square regression and the random forest regression. For leaf chlorophyll is the KNN, K nearest neighbor regression and the partial least square regression. So now, using the best, so we selected PSLR as one of the best retrieval algorithm to now do the estimation of LAI and chlorophyll across the park. So these are the generated maps of the chlorophyll and LAI distribution across the park. And what we found, without integrating the active learning methods, is that there was an underestimation of LAI looking at the range, and therefore the pattern that is shown here of the LAI is not realistic. So, because it suggests that there's generally a low biomass across the park, which is not the case. However, when it comes to the chlorophyll estimations, this one is much better in terms of the realistic, in terms of the patterns. The patterns are more realistic because what we know is that on the northern part of the park, it is a low-lying area where you find a lot of grazers. That's where animals are feeding, also on the eastern lower parts of the park. And you can see that the chlorophyll, the predicted chlorophyll there, it shows higher ranges. So it shows there's quality forage and also species diversity in the area. Now, we incorporated the active learning methods to see if they will improve on the retrieval accuracy. So what we see now is there is an improvement in terms of the relative root mean square error looking at the chlorophyll estimation, chlorophyll estimation and leaf area index. So looking at our relative root mean square error is way much better than when the active learning algorithms were not used. And therefore, so when the partial least square regression is integrated with the residual active learning method, it gave the best retrievals. We can see with the relative root mean square error of 39% and chlorophyll of 16%. And also we saw an improvement on the R square, which shows an improved variability by the model. So this is also what is happening in the background when these active learning methods are selecting the labeled samples. So what you could see with the best, incorporating the partial least square regression with the best active learning algorithm, we can see here, for example, this RSAL is the residual active learning, is the one that gave the best samples, informative samples, into the partial least square regression for it to have accurate retrieval. So we can see, looking at the graph, that it quickly, just with from 100 samples, which is the subset that it started with, all the way to 200, we could see a drastic reduction in terms of the RMSE for RSAL, which is way much better than the other retrieval algorithms. This is my last slide. I'm told that I have to wrap up now. Okay, so, and then we did the estimations, and then I quickly want to draw your attention to the LAI. We see an improvement in terms of the estimation of LAI looking at the ranges. The patterns are more realistic, and they also show areas of moderately high to low biomass. And as for chlorophyll, it's still the same. So in conclusion, the results of the active learning methods integrated with the partial least square regression, they showed an improvement in the chlorophyll and the LAI retrievals corresponding to the relative root mean square errors of 16.58 and 39.87. The spatial prediction of the maps appeared more realistic, and the range values, they came close to the field data range. These findings highlight that these radiative transfer models may require local parameterization in order to simulate the multi-species canopies accurately. Lastly, these findings have significant implications for the development of transferable rangeland monitoring systems. I thank you.
Thank you for that interesting presentation, Dr. Tsele. And just one thing, as an active user of Sentinel-2 data myself, I think it would be interesting to see the integration of the triad feature selection algorithm, which we saw a few days ago, together with the active learning and the machine learning to see how we can do predictive analytics and also classification. So moving on, our next presentation, our next presenter is Ms. Yolanda Tumalo. She's the founder and CEO of YASI, which is an aviation and aerospace engineering company, which focuses on drone and satellite solutions. Ms. Yolanda will be presenting on improving the efficiency of LoRa IoT devices with AEM systems and AI techniques. Join me in welcoming Ms. Yolanda.
Hello. Okay. Where am I pressing? Okay. So this is. Oh, okay. Okay. All right. So since I've been introduced, I'll pass a lot of things. So my presentation will just describe the different technologies that make up the integrated system and speak on the benefits of the industries, how industries can benefit. So LoRaWAN is a low power, long range, and open source form of communication protocol. And its performance is influenced by 4 factors: the spreading factor, the power consumption, the channel occupancy, and the rate. The channel occupancy rate and the distance between the gateways. And what we are then working on is the ambient energy management system. In this particular diagram, we have solar cell and batteries, which is a combination of the different energy sources, which makes it a hybrid energy storage system. And you find a microcontroller. So if you increase the transmission power, the power transmission, then you increase the range of how far you can send your data. However, the power efficiency decreases. But if you increase the duty cycle, then you're able to send more data, but that also minimizes the efficiency, which is why we are working on the hybrid energy storage system, so that because the power, sorry, I'm very nervous, excuse me. Because because the spreading factor and the channel occupancy rate and the distance between gateways is also influenced by the power consumption, which is why it's very important we work on the hybrid energy storage system. So currently what has been done, supercapacitors and the lithium batteries are able to then extend the combination of them are able to then extend the battery life, and it's used on wireless sensor nodes. The combination of solar cells and TEGs are able to then, the TEG is able to offset the solar, so that the Power Watch 2, I don't know if any of you know it, it's a smartwatch, it doesn't require any charging. And if you combine fuel cells and electrical batteries, then the drone can go much further at a lower cost. Okay, so where does deep reinforcement learning come in? So as I said, the spreading factor is one of the factors that influence the performance of LoRa. And if you increase your spreading factor, you are able to then communicate much further, but you are unable to then, the data decreases and vice versa. The same thing with duty, with power transmission, as I explained. You increase you increase your power transmission, you're able to then increase your range, but then it also has a lot of interference. If you increase your duty cycle, you're able to send more data, but the power efficiency goes down. So, and also with the occupancy, if you add more devices, then obviously you're able to scale up and you're able to monitor more things, but it also has the negative effect because it also increases collisions and it results in packet loss. The same thing when you increase the distance between gateways, you're able to cover greater distance, but it also has negative effects in terms of occupancy. And with deep reinforcement learning, we're then hoping that those trade-offs can then be minimized through deep reinforcement learning, using those metrics, such as, especially with power consumption. I'm just going to go back to power consumption because that's where we actually are. If I increase if we enhance the power of the battery by using hybrid energy storage system, regardless of which energy source we're harvesting, we're able to increase the data rate and the range, so we don't have to compromise between data and the range. However, in terms of power efficiency and in terms of packet loss and interference, those are still would be a problem. So with deep reinforcement learning, then the machine can help itself to better overcome those problems. So I'm just going to come back to this slide if I have time at the end. So last month, so we went to the BRICS Youth Energy Summit. And one of the sites that we visited was the landfill waste to energy power plant. And what we found there, what struck me at least, was the fact that the plant that is responsible for minimizing load shedding cannot support itself. And then, fortunately for this particular plant, it's off the grid of load shedding. However, the other two plants, they experience load shedding. So the renewable energy plant that is meant to minimize load shedding cannot produce power to minimize load shedding because it also gets load shed. So, and another thing is that in this particular plant, the engine failing is normal. They do have a automated switch off whenever there's too much oxygen that goes through the pipes. So it switches off. So these are some of the monitoring systems they have, which obviously then now minimizes the efficiency of the plant, because if the engine trips, and that means that you can't produce energy at the time, and then the engineers must then come. So the person has said that they can't have enough, they can't have too many monitoring systems because that would be expensive. And this is where LoRa comes in, because LoRa is an open source, which means it's free communication. Besides the fact that obviously when you send to the satellite, that's not free, but it in of itself, in terms of terrestrial communication, it is free. So in terms of improving energy efficiency of plants, that's where the integrated solution comes in. And also, in terms of data analytics, it then will be in a position to assist and provide recommendations so that the power plants that are meant to minimize load shedding can then get to a point where they can then sustain themselves through data analytics. Another project that I'm personally involved in is the Digital and Drone Solutions project, which was supported and funded by Department of Science, TIA, Liminal, Newton Fund, and Innovate UK, and with the support of Black Business Council. and in collaboration with Operator, which is a drug developing company, University of Cape Town and South African Medical Association. So the project had three parts: helping to improve medical adherence for patients in chronic medication. We had a clinical trial for epilepsy, and also obviously medicine drone delivery. And so these are some of the wearable devices that were meant to then monitor the patients and assist in terms of the drug development, because you obviously need to monitor the disease progression of the patient, and also how the patient responds to the medication that is being, that they're being tested because it's a clinical trial, so that you can minimize the side effects, and also the smartphones and drones. So all these particular devices, they require power, they require communication. And what is interesting with the Scale Out for Impact, it was actually meant for low income. So we were actually supposed to be working in a rural area. But because there's no communication infrastructure in terms of internet, we ended up obviously working with Red Cross Memorial Hospital in terms of clinical trial, which is actually in the suburban area. And part of the monitoring system was also like my diary, where the patient then has to say how they're feeling that day and all of that, so that in parts of the clinical trial. Why am I saying this? Is because when we talk about monitoring, this is where LoRa also comes in. The wearable devices can use LoRa in terms of communication and in terms of power, because if you don't have power, you're not able to then get the information from the patient so that you know how to then properly respond to it. So it's not just about, and these are some of the publications that came out of the study, it's not just space communication or forest fires, it's also health, and in terms of drug development, and in terms of vaccines, when we talk about satellite communication. And this, in terms of advanced data analytics, these are some of the problems that it can then solve, the applications. And in terms of these, agriculture, in this particular one where you have cows, this will obviously be a high occupancy rate, which means that as much as you can, you need to obviously scale up, because you need to monitor where your cows are, you need to monitor their health in terms of the temperature, the pressure, the blood pressure. However, there's a lot of collisions and packet loss in this regard, which is where AI and deep reinforcement learning can come in to then offset the negative effects of being able to then apply the technology. And where am I? Where are we now? So this study emanated from my master's, doing satellite systems and applications at CPUT. And we are obviously now working on, publication, because that's part of the master's requirements there at CPUT. And then we've also had some positive feedback from SANSA. I've spoken to SANSA, and we are looking for collaborators. And in collaboration, it's not just in terms of technology collaboration, but also user cases. And as I explained, remote sensing is not just limited to environmental monitoring. It's also within health, it's also within business, it's also within energy. Everything that we do, that's what direct to satellite Internet of Things goes. So I just want to come back to this particular slide. Okay, so how does it then now work? So the LoRa sends the signal directly to the satellites. Right now you have SWAM, you have Lacuna. Those are all satellites that are in the remote sensing, and they have the LoRa gateways boarded on them and cloud servers. And from there, it then goes to the application server or their particular server to then be able to then process it. That is a development because Currently, in terrestrial, there's LoRa, it goes to the gateway, then it needs internet to go to the cloud server, then from the cloud server it still needs so that this whole relay, it minimizes it, because from here, you just go to the LoRa, which is on the satellite, and from there, which also has a cloud server, and obviously the coverage is much greater, and then goes to your application server where the deep learning reinforcement can go. So yeah, in terms of efficiency, that's how efficient it will be, or is, and thank you.
Thank you, Yolanda, for that presentation. So our final presenter is Habo Motapo, who is the CTO at Motseni High-Tech Space. MHT develops and designs automatic identification receivers and transmitters. Habo will be presenting the development of MHT's automatic identification system receiver and upgrade to VDES and Blue Force Tracking AIS. Please give a warm round of applause for Habo. Thank you.
Good morning or good afternoon, everybody. Okay. Yeah, my name is spoken. I'm Habo Motapo, Technical Director with the background in satellite engineering. I've got more than 10, 15 years experience designing and developing satellites and satellite subsystems. So our company, Motseni High-Tech Space, specializes in the design and development of subsystems like GNSS radio occultation receivers for weather prediction, space weather monitoring, tech, RF microwave subsystems, satellite GTNC transceivers, radar subsystems, intersatellite links, transceivers, terrestrial and satellite AIS, VDES, maritime monitoring systems. So AIS, as most of you are aware of it, it's been mandated by IMO to be carried on shipping vessels of certain gross tonnage. And it's an exchange, AIS it's used for exchanging information between ship and ship and ship and shore. And of course, the satellites can be able to pick up those signals from space too. So different kind of messages are transmitted by AIS, like static, like MMSI, IMO, dynamic messages, position, timestamp, UTC, course over ground, navigational messages like destination of the ship, expected time of arrival, and the cargo type. But of course, it does have some limitations in terms of coverage, and the system is getting overloading these days. It's bandwidth limited, and it does not have duplex communication. That means satellite can't communicate with the ship. Only the ship can communicate, and satellite can hear and transmit it somewhere else. So this is how the system uses time division multiplexers, which a frame is divided into time slots where the ships transmit within each slot, which is around about 26 milliseconds. So the ship will communicate with the ship with AIS, and then the satellite will pick it up, but the satellite can't communicate down with it. With that. So we're developing our AIS using software-defined radio principles. And this is the fun part of it, because we used to, talk about all this maths. We hear a lot of young people saying all the maths we're learning in high school and universities, what are we going to use it for, But in software-defined radio, we use, those trigonometries and the Euler equations. They work magic, in signal processing to process all these signals, in communication systems. So what happens is that when AIS is transmitted on those two frequencies, 161.975 and 162.025, so what we do is we down convert that signal, down to a low IF. And then using complex signals, the Euler equations, then we got a positive and a negative frequency. And then we can take we can generate a negative carrier or a positive carrier. So if we generate a negative carrier, we can be able to shift this spectrum to the left, so that you can be able to center on this one and then be able to filter it and process it. And then if we use positive carrier, to down convert it, then you can be able to shift that same spectrum to the right, and then center on this signal, and then we digitize it with analog digital converters, and then from there we can process it, in software, digital signal processor. So you can have nearly like brick wall filters, elliptic filters that can filter that signal. Unlike with analog electronics, you can be able to generate certain filters. Then we demodulate it, and then suddenly you can see AIS signals appearing. Then we filter it. Then from there, we can be able to extract the messages, which are transmitted by the ships. But the beautiful part about this is that those two signals, AIS is transmitted on two frequency channels. We can demodulate those frequency channel, two of them at the same time, and be able to extract all those messages, simultaneously using all these digital signal processing principles. So we have demonstrated our AIS, concept demonstrator to AMSCO and IMT and other organizations, and then we took it to the sea, connected to the antenna, and then receive all those signals from the ships. And then we're able to extract a lot of these VDM, AIS messages. And then we develop algorithms, we decode them, and then we can extract all those MMSI of the ships, And then from here we get the MMSI and the latitude and the longitude of the ship, and then we can be able to display it there. So if the ship is moving, you'll see, the latitude changing, and then you can be able to track those ships. So yeah, that's our, we plan on prototype, because in our company, we design, and then we take our systems through schematic design and PCB design, and we're going to prototype this AIS. Okay, but like I mentioned, that AIS is limited in bandwidth. There's a new system that's coming now called VHF Data Exchange System. So this is the next generation, they call it AIS-2. So it's a maritime communications, designed to deliver two-way communication. Like we said, with AIS, the satellite cannot communicate, with the ship, but with the VDAS now, the communication system is going to be between ship and shore, ship and satellite, satellite and ship, satellite and shore. So it's a whole network, communication system. So it's a complement, of course, to the terrestrial and space-based. So the IMO and IALA, they're busy testing this. That's why if you follow space news and industry here, companies are launching satellite with VDAS payloads, so that they can be able to test, the downlink segment and even the terrestrial segment. So the system is being currently tested. It's not yet deployed. So at least we are part of it. We're developing it, that system ourselves too. So as I said, it's ship to ship, ship to shore. Of course, it includes GNSS receiver and antennas. So it's a multi-component system that includes AIS, ASM, which is application-specific messages, and VDAS, VDA terrestrial and satellite. So this is how the system works. So the satellite can transmit to the ship, ship to the satellite, ship to ship, and ship to shore, and shore to satellite, satellite to shore. So the maritime industry is evolving in communication too. So these are just from the technical specification from ITU of the various frequencies which are used for, there's a band of frequencies for ship to shore and shore to ship, so that there's no interference. So because we are upgrading our AIS to VDAS now, so when working in SDR principles, so we started with the VDAS, part of the VDAS, which is ASM1. So VDAS, ASM terrestrial, and VDAS ASM, that means AS2 terrestrial and terrestrial 1. They've got a certain packet format. So each of these, their packet format is not like AIS, it's different. And the packet format for the satellite, like ship to satellite, is different from ship to ship. So but they use forward error correction in this, and the satellite one uses some pilot signals in there. So this, okay, each of these, like I said, VDAs, from ship to satellite and satellite to ship, each uses each unique synchronization weight, and then, but the identification and location of the active station is still reliant on the AIS. So because it's a multi-component system including both AIS, ASM, and VDAT, it's still giving preference to AIS, followed by ASM and by the terrestrial one. So it uses modulation coding schemes and the link identities, that defines the channel configuration as the communication is taking place between all these complex systems. So the data still has to go through the CRC calculation and interleaved with forward error correction, encoded, and then scrambled data, and then bit mapped. So VDA ASM link ID uses the parameters is the pi over 4 QPSK modulation. Because the AIS uses GMSK, but this one, and then the VDATER link ID parameters uses pi over 4 QPSK and 8 PSK and 16 QAM. So for us, in order to develop, this, we have to be able to implement all these modulation schemes. And the VDASAT link ID parameters use pi over 4 QPSK, BPSK, and QPSK CDMA. But it was an advantage for us CDMA because one of our products is a GNSS radio occultation receiver that we receive GNSS signals that uses CDMA. So we've already, processed the spread spectrum signals. So, as we said, our approach is through the SDR, and from the technical specification, this is how the VDAS transceiver operates. It's got an agile transmitter and then 6 receivers. So in SDR, we can be able to implement all these 6 receivers in software, and then implement them on the FPGA or ICT, like that. So what we do is as the signals are transmitted, because it can either be from the satellite or from the terrestrial or for ASM or for AIS. So these intelligent receivers will, able to detect, okay, this one is for the AIS, this one is for the VDA terrestrial, and then take it over to the presentation interface. And the transmitter take data from the presentation interface, modulate it, based on the information given, whether is it for ASM or for terrestrial. So we developed the OC layer, in our company. We implement transport layer for AIS and VDAS, network layer, link management entity, and data link services. Medium access control, still looking for software engineers who can help us with that. We developed the physical layer, and ASM operated bitrate of 19.2K pi over 4 QPSK. Transmit power is 1 watt, and high power is 12.5 watt. Okay, so we implemented pi over 4 QPSK, simulated it, and then that's the, yeah, I'm finishing. Oh. Okay, yeah, okay, I'll just be quick first. This is the implementation of the QPSK, and then be able to, that's the, engineers guys will know, the constellation, and then we received the messages. 8 PSK, we did the same with it, received it, and then we did the same with 16 QAM, received it, and then we were busy with the Blue Force tracking AIS. That's the one that, there could be a requirement by the Navy or the Coastal Guard, to perform AIS communication out of public AIS, wherein they can feature, where they can see other ships, but the other ships can't be able to see them, more like John Cena say, you can't see me. So this, an example would be like boats in Group A, they can only hear each other, and these ones, they can't hear those ones, and, they can't hear those ones. So what this does is that, it's got different modes of operation, where in the Navy, they can communicate among themselves, they can be able to hear those other guys, and be able even to command them if they want to. So it's got different kind of modes for operation. So it can have normal mode, send, receive, open AIS, and then receive, mode where it receives only AIS and EIS, and then restricted mode when the transponder transmit only EIS and receive both of those sometimes. So thank you very much, and I would like to thank you and thank my team at Mtsweni High Tech Space.
So unfortunately, we have reached the end of the session. Do we have time for questions? Okay, unfortunately, we don't have time for questions. However, there is one question I see regarding the MicroStar. So at the conclusion of the session, then maybe people from the audience can come and engage some of the presenters. So to the presenters, thank you for your dynamic your presentations. They're quite informative and I quite enjoyed them. And to the audience, thank you and enjoy the rest of your day and enjoy the rest of the conference. A round of applause to the presenters.
Thank you so much to you, Dr. Naeem Aji, Environmental Science Senior Researcher at SAPI Southern Africa. A round of applause, please, for the panel. Just before we invite the presenters up for the gifts and the picture, the theme for today's conference is all about space and the future. And I was told that on the first day, there was supposed to be a youth session at the end, and unfortunately, those youth didn't get to present. And there was a presenter who came earlier that said there's not a lot of youth represented here today. So they've come and they've spoken to us, and we're going to give him an opportunity to speak. I ask, since the youth are the future of our industry, that we give him the gift of our time and attention. He'll come immediately after lunch, and I'll definitely introduce him then. Speaking of lunch, it's going to take place in the same place as it did yesterday, so please can we be back and ready for our youth at 2:15. It is now 13:33, and whilst that is happening, we will do the gift giving and the pictures. Thank you so much, and we'll see you at 2:15.